So this permutation looks like this, and we want to know how many ways are there to add elements to that permutation. R elements. So I will first define P tau R K, the number of permutations in S, size of tau times K plus R that contain tau to the K. I guess I may not have actually defined tau to the K. That means the direct sum of K copies of tau. Okay, and the main result is that P tau R K is eventually polynomial in K. Meaning, there's a polynomial that coincides with this for all large enough K. Now,
and you know the degree, and you know where it stops?
Okay, yes, we know the degree. I have a bound for where it starts. The bound, I haven't been able to make the bound sharp yet. I mean, based on experimental data, we know which one it should start with, but the proof doesn't give us that. But it can probably be adjusted to do.
But you can find a place where it definitely.
I can find it, yes. The proof I'm gonna outline pretty briefly, because it's too short to talk to do the whole thing, is it gives us a bound on when it eventually is. And furthermore, not only do we know the degree bound in that, we also know the first three. So I'll say theorem 2, because this one is also interesting enough to be called a theorem, I think, is that P tau R of K times size of tau. So here I'm multiplying it by a constant. So this is just the number of elements in tau to the K. Does not depend. I started this wrong. So I'm going to look at this, but I'm going to say the first three coefficients, the leading three coefficients of P tau R of K times size of tau do not depend on tau. So in other words, we can find the first three coefficients just by doing what we already know how to do, getting the corresponding polynomial for the increasing permutation. Because it doesn't matter which permutation we choose. And 3 here is Shar. So,
and can you easily determine the next coefficient depending on tau?
I don't know of a way to. So I don't know anything beyond the first three coefficients, because I won't have time to talk about this, I guess, but it's in the thesis. The way you prove it, to prove the first coefficient is the same requires a result about codimension 0. To prove the second coefficient is the same requires a result about codimension 1. Third coefficient requires a result about codimension 2. And there are no results about codimension 3, so I don't know how to prove anything.
Not yet.
Yes, if somebody proves something about codimension 3, it would probably tell us something about the fourth coefficient.
If somebody should be you.
For the vote of confidence. Okay, and just to give you an example of what these polynomials look like, P132, this is codimension 4, permutations 132. I'll write n for k times tau. So this means if you want the one of length, the number n plus r, you have to plug n into here. It is 124 n to the 8. Now, when I'm writing this down, I should say, this is not yet rigorously proved because we don't have the tight enough bound on the but I'm like 99.9% sure it's true. And by generating, all you need to do to prove this rigorously is to generate a few more terms of the sequence, and if they correspond, then it is a proof. I didn't feel like working my computer that hard. I'm running out of space. Good thing the polynomial is almost over. Okay, and by comparison, P231 for n equals, the first three terms are of course the same, then 10 thirds and 5. So the fourth term can differ. $595 over 18 n squared minus 50 thirds n. Yep, they can be negative. Actually, it can be negative just for the increasing pattern, but they can be negative. So this is the kind of result we get. Also, I should say for the increasing pattern, there are various ways of interpreting the first few coefficients. This one, the first few follow a nice formulas, but we don't know anything, or I don't know if it is known, but I'm not aware of anything for, let's say, the trailing coefficient, which has interesting numbers, but I don't know what those numbers are.
What do you know about the denominators? How big can they get?
That's a good question. I don't know anything about the denominators, I guess. I suspect they can get pretty big.
So the constant term is obviously always an integer.
The constant term is not obviously always an integer.
It is an integer, not obviously.
All of the ones we generated for the increasing pattern were integers, and that makes me want to conjecture that it's always an integer, but I can't even prove that. Remember, it's only eventually polynomial. You can't plug in 0 and say, well, obviously it's an integer for 0, because it's not only eventually polynomial. So, very sad, we can't even prove that that's an integer. Or I can't. Maybe you can. Okay. So I'm going to state basically the method that we use to prove this. And the methods are more interesting than actual proofs anyway. So it's probably a good idea, good thing I don't have time to talk about the whole proof. So the method is prefix schemes. So I'll talk about what this means. Basically, I will define Q, tau, R, V of K. So I define P, tau, R of K to be the number that contain tau to the K. And I'll define Q, tau, R, V of K is the number of I in S. K is like tau plus R. Containing tau to the K. And starting with the elements V, which is equal to V1. Some number of given elements. So basically I've broken down the problem in a massive way. I've just broken it down based on the first few elements. And here's so I could write very easily that P tau R is equal to Q tau R1 of K plus Q tau R2 of K plus etc. Summing on the first element. Or I could sum on the first two elements. So I can break this down arbitrarily. And of course, once I've given all the elements, it's either 1 or 0 for each one. But we need a more systematic way to do that because there are way too many cases. So this board is really tough to pull down, but I seem to remember it being even harder in the past. Maybe they fixed it.
You get slunk on.
All right. So what we're going to do is basically create a branching diagram that looks like this. We start with P, which is Q tau. I won't write tau R because I'll just assume that those are. I won't write tau. I'll write R. And the vector of starting elements that are required is the empty set. So then I'll do Q. I'll break this down to QR1, QR2, QR. The largest possible element here is k size of tau plus r. And each one of these will branch into several cases and so on. And if this went on forever, we would not be able to solve anything. But the method of the proof is to show that this doesn't go on forever. One of a few things has to happen first. So the main escape hatch from this going on forever is perhaps we can prove that some of these are equal to some Q function of lower codimension. So maybe this one is equal to Q r minus 1 of some vector. And then, assuming we've proved the result already for codimension r minus 1, this is eventually polynomial. So that's nice. That will say that some of these branches are just polynomials. Unfortunately, this won't happen to every branch. So the other thing that we would like to happen is for perhaps somewhere out here, I have Q, R, V, and I will prove that this is equal to Q, R, W, where W is shorter than V. And in particular, a prefix of V. So either we get escape to lower codimension, or we wrap around. And this by itself would not prove polynomiality, because there are many recurrences that wrap around like this, where the solution isn't polynomial, like the Fibonacci sequence. But if you have a recurrence of the form Q, R, if you have a recurrence where Q, R, V of k equals Q, R, V of k minus 1 plus polynomial stuff, then the solution to this is guaranteed to be polynomial. That's by the theory of linear recurrences. So what we will have to do is this will wrap around, and we will prove that this is Q, R, V of k minus 1. So in other words, and also there can only be one of these. There can only be one path from each thing that wraps around to itself. Otherwise, you would have a recurrence with some characteristic, some eigenvalue that's not 1 or minus 1, or in this case 1, I guess. So it's a pretty restrictive thing. And let me see. I'd like to outline how this works, but I would also like to prove that the coefficients are the same. We don't have time to do both. Okay, I'll outline how this works. So I want to make a point about these repeating patterns. Repeating patterns, by their nature, live near the main diagonal of the permutation graph. At least for large enough k, right? This is if I have really large k, here's my repeating pattern. It all lives near the diagonal. So let's say that the very first element of the permutation let's say I happen to have a permutation and the very first element is way, way off the diagonal. It's a large number. Well, that cannot possibly be included in one of these repeating patterns. The elements of the repeating pattern need to be at least near the diagonal. They can be off it by up to r, where r is the codimension, but they need to be within R of the diagonal. So if we divide this into two regions, there's the off-diagonal region and the diagonal region. If my very first element is off the diagonal, then, okay, I know it's not part of the permutation, so by an argument that I don't have time to go into in detail, you can delete that element, and now you have one lower codimension, because you just removed an element that wasn't involved in the pattern. So this is one of the ways of reducing the codimension. The other way of reducing the codimension is much more involved, and this happens when elements are put on the diagonal. So imagine that we don't have any, that we're creating a prefix for my, so I'm calculating Q, R, V, and R, and V is one of the prefixes, and it's pretty long, and all the elements in V are near the diagonal, so I can't say any of them can be thrown away. Well, V might not actually be an element, it might not be a prefix of the repeating pattern. There might be some elements in V that have to not be part of it, but I can't say which they are necessarily. So let me give you an example. If the pattern, if tau equals 1, 3, 2, and V equals, or sorry, tau is 1 and V is 1, 3, 2, these can't all be part of the tau to the k because, well, they're not increasing, but 1 and 3 can, or 1 and 2 can, I don't know which is which. So most of the issues come from dealing with this. So the proof consists of building the tree, looking at the prefixes, and so for some prefixes, you can prove that an element can be removed. For others, you can't prove that an element can be removed, but you can create a monovariant. Actually, I have 3 different monovariants, A, B, and C. And you could prove that one of these has to increase. And so these monovariants are increasing, and each of them has a maximum value. So eventually all the monovariants will be at the maximum value. And at that point, one of two things has to happen. Either you can get rid of an element, or you can delete, or you can basically do the reduction that I said, where, so when all monovariants reach maximum value, which is R. I don't have time to define them, but I wish I could. Then QR K is going to be equal to K minus 1, or you're going to be able to delete something. So this is the outline of the proof, and I'm running out of time. I've got to respect the 48-minute limit. Thank you.